All right, this is part 2 of section 3.3. Now we're trying to determine where a function is increasing, decreasing, or constant. Okay, so a function is increasing. So say we take this first graph here. So we have two areas in this graph where the function is increasing. So from here to about this point right here, and then from here to about, it goes on forever. Notice how the graph is going upward, and we're reading from left to right, is going in this upward direction. But notice you're decreasing from here to here. We're going downward. Okay, so if your function is basically, if your function has a positive slope, well then you're increasing. If your function has a negative slope, you are decreasing. And if you have basically a horizontal line like you do over here, well then that means that you have a constant. Your function is not changing at all. It's not going up or down. It's just right there at that horizontal line. Okay, so a value of, so here we're looking at local extrema, a value of the input where a function changes from increasing to decreasing. Okay, so we were increasing, then we changed to decreasing. Kind of like right here, we went from increasing, increasing, increasing. Okay, well now we're decreasing, decreasing. Okay, where that change happened, which is, let me get rid of all this, about right here. Because over here you're increasing, on this side, well now you're decreasing. Where you change from the increasing to decreasing, we have a local extrema there. And the type of local extrema would be a local maximum. Okay, now we're going to talk two different types. We're going to have an absolute maximum and we're going to have a local maximum. So within this area of the graph, there's a local maximum. Now, if you go from decreasing to increasing, so say like we do here, okay, decreasing, 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 okay, now increasing, increasing. Where that change from decreasing to increasing, which is about right there we have something called a local minimum. Okay, now it's not the smallest value of the graph, but within that area of, say, between here and here, well, yeah, that is the smallest value within that area. Okay, so together the local maximum and the local minimum are called the local extrema, or the local extreme values of a function. Now you can also change the word local and replace it with relative. So we could have a relative maximum or a relative minimum or relative extrema. So if you're talking about a constant function where it doesn't have increasing or decreasing intervals, well then that function, since it doesn't have increasing or decreasing intervals, it won't have extrema either, because the point of extrema is you have to go from increasing to decreasing to be a local maximum, or from decreasing to increasing to be a local minimum. And since the constant function doesn't have increasing or decreasing intervals, therefore it cannot have local extrema. Okay, so here's just a graph looking at the local extrema. So we're going from, this is increasing to that point. From this point, okay, now we're decreasing. So at this point right here, that means that we have a local maximum. And what we say is we have a local maximum at the y value, and the y value is 16. And that local maximum occurs at the x value. The x value is -2. Okay, and we have that right here as well. So we have a local maximum at 16, and it occurs at x equals -2. Now we'll go from decreasing to increasing. So at this point right here, I have a local minimum. So we say we have a local minimum at the y, and it occurs at the x value. So for the local minimum, we have a local minimum at -16, and it occurs at x equals 2. Okay, so here's the formal definition for local minimum and local maxima. A function f is an increasing function on an open interval. So open interval would be something like this right here. Notice how we've got arrows on both sides. It goes on forever in either direction. So our domain would be from negative infinity to infinity. So we're not bound in it. We're not saying, okay, the interval goes from -4 to 1. It doesn't say that anywhere. Okay, so if we don't have that restriction, we're saying we have an open interval. So if we have an increase in function on an open interval, and if f of b is greater than f of a for any two input values, a and b, given that b is greater than a. Okay, so b has got to be greater than a. And also, so this is talking about, basically, this is talking about the x values here. These are talking about the y values. So if you have one x value bigger than the x value, and then when you plug both of those x values into the function, and that y value for x is bigger than that y value for the next x, let me show you on the graph, because that can become very confusing. Say that, let's see, b has got to be bigger than a. So we will say that here's our b, here's our, actually let me move over just one. We'll say that here's our b and here's our a. Make sure I'm still on the graph. Okay, so here I'm saying that b is 4 and a is 2. So f of b, you need to go up here, looks like it's 16. Okay, so this is f of b, which is 16. Now I need to go to a down here, looks like it's -16. That's f of a. So we know that 4 is bigger than 2, and we know that 16 is bigger than -16. So because of that, so we have b is greater than a, and then f of b is greater than f of a, that 16 is greater than -16. So because of that, we have an increase in function. And notice that we are increasing from here to here. That's an increase in function. If we look at decreasing, okay, a function f is a decreasing function on an open interval if f of b is less than f of a for any two input values a and b in which b is greater than a. So let's use the same ones. So we'll use this graph again. Okay, so it says that b has still got to be bigger than a. So we'll say, let's see, we'll say this is b. We'll say this is a right here. Okay, so b is 2 and a is -1. So 2 is bigger than -1. Okay, so that's met. And then I need to go down. So this is f of b. So f of b is -16. Okay, a looks like it's 12. So this is f of a. And notice that f of b, the -16, is smaller than f of a, which is 12. Oops, wrong one. Okay, so f of b is smaller than f of a, and we have that b is greater than a. So we should have a decrease in function, which we do. From here to here, this is a decreasing function. Okay, a function f has a local maximum at x equals b if there exists an interval from a to c, with a being smaller than b being smaller than c, such that for any x in the interval a to c, f of x is less than or equal to f of b. Okay, so first of all, it's talking about a local maximum. So we can talk about this point right here. So we got a local maximum at that point. So say our interval goes from -3 to, we'll say, -1. Okay, so our A is -3 and our C is -1. And this right here is our B, since that's our local maximum. Now notice right here, so our local maximum occurs at a -2. Just drop right down. It occurs at a -2. Okay, so we know that -3 is less than -2, which is less than -1, which in our case, that's A is less than B is less than C, just like it says over here. Okay, that's all that's saying. That B is, this point right here, is bigger than all of these X values over here, and it's smaller than all these X values over here. That's basically what it's saying. And then the other part of it, it says for any X value within that interval. So any X value between -3 to -1, any value that you can choose. Let me get rid of most of this. Okay, so any values between -3 and -1 in that interval A to C, that's basically what it said, f of x is less than or equal to f of b. Okay, so that's talking about our y values. So at this point right here, B, this would be f of b. Now any of these right here, this would be f of x, because you would go from, say, this point right here, there's our, actually let me use, from this right here, there's our f of a. This point right here, there's our f of something else. Okay, each one of these until you get up to b, not including b. Okay, so all of these points right here, those would be f of x, because we could choose any x value between -3 and -1. Now notice how all of those fall below f of b, or that are smaller than it. So f of x is smaller than or equal to f of b. So if you have that, those two, a is smaller than b is smaller than c, and any x value within that interval, the y values are going to be below the y value for your maximum. Then you have a local maximum. Okay, and then switch gears, we'll talk about a local minimum. So at x equals b, if there exists an interval from a to c, so let's go ahead and come back over here and we'll look at a local minimum, which is right here. Okay, so we'll look between 1 and 3. That will be our interval. And it says that'll be A, this will be C, and this is our B value, which looks like it's at 2. We know that 1 is less than 2, which is less than 3. So that's our A is less than B is less than C. Okay, got that. And then it says, let's see, such that for any x value between the 1 and the 3, f of x is bigger than f of b. Okay, so any x value between this 1 and this 3. So if I choose 3, it goes to -8. If I choose this value, it goes to somewhere between -16 and 12. This value looks like it goes to 12. This value looks like it goes between -8 and -4 somewhere. Okay, but notice for f of b, that is -16. So that is f of b, so -16. Now notice all the values are above -16. So for all of these values here, these are f of x. And notice how all these values f of x are bigger than the f of b, which is what this is talking about. F of x is bigger than or equal to f of b. So if we have those two, then we're talking about a local minimum. Now this is just the formal definition. We don't have to go through all of this for us to find that. If we have changing from increasing to decreasing, hey, local max. A change from decreasing to increasing, hey, local min. And that's it.